Assalamualaikum warahmatullahi wabarakatuh, and very good day. So for this part, we will discuss about a mixing chamber. Okay, in terms of function, okay, the function of the mixing chamber is mixing streams of fluids, and also can be used to exchange heat through mixings. So actually, this mixing chamber also we can consider as a direct contact heat exchanger. So in this figure shows an example of a mixing chamber, where the specific name for this system is an open feed water heater. So you can see we have two inlet for the device where the steam enter at the first inlet, and then we have second inlet where the condensate water enter the device and mix together in the chamber and come out from the device through the outlet, and we will have what we call a mixing fluid that considered as a hot water. So in terms of schematic diagram, we can draw the simple schematic diagram as shown in the slide, where we have some sort like a tank with two inlet and also one outlet. So at the first inlet, we will have steam. At the second outlet, we have condensate water, and at the outlet, we will have hot water. Okay. So in terms of process inside the device or inside the system, we will have a mixing of fluid, and due to the temperature difference for each fluid, so we will have the fluid will exchange heat throughout the process. Okay, now in terms of characteristics, so for the first figure, the figure shows the what I call the schematic diagram, simple schematic diagram for the mixing chamber, and the right hand side schematic diagram shows the application of the mixing chamber, one of the application of the mixing chamber. So T elbow also can consider as a mixing chamber, where this T elbow will use to mix two different fluid, where here we have hot water and also cold water combined together to produce warm shower that can be used in our bathroom. So in terms of characteristics, so rate of heat transfer Q dot, due to the well insulated condition of the mixing chamber, so no Q in, no Q out from the outside to the mixing chamber or from the inside to the surrounding. So the rate of heat transfer Q dot will be 0. Okay, in terms of rate of work W dot, no work done because no we call the mechanical movement, rotating shaft, fan movement, and so on. So for the mixing chamber, so no work done, so W dot will be equal to 0. So in terms of potential energy, so the potential energy change will be can be neglected for the mixing chamber. So delta PE equal to 0. Similar goes to the kinetic energy for the mixing chamber. So we can neglect the what call the value of kinetic energy change. So delta KE equal to 0. Okay, so when we implement the energy balance equation for steady flow process, so we will have this full equation. So based on the what I call mixing chamber condition in terms of heat transfer, so we can cancel out the term that involve the term in the energy balance equation for the mixing chamber. So for the mixing chamber, due to rate of heat transfer equal to 0, so Q in dot, Q out dot will be 0, and no work involved, so W in dot, W out dot also will be 0. And due to the what I call the negligible change of potential energy and also kinetic energy, so the term for kinetic energy and also the term for potential energy also can be neglected in the energy balance equation for the mixing chamber. Okay, so the remaining term is only the E mass in and also E mass out in terms of enthalpy value. So we have total in M dot H equal to total out M dot H for the mixing chamber. Example 4.10, consider an ordinary shower where hot water at 60 degrees Celsius is mixed with cold water at 10 degrees Celsius. If it is desired that a steady stream of warm water at 45 degree be supplied, determine the ratio of the mass flow rate of the hot to cold water. Assume the heat losses from the mixing chamber to be negligible and the mixing to be taking place at a pressure of 150 kilopascal. So we just draw the simple schematic diagram for the mixing chamber, and put the data at the inlet, outlet, at the inlet of the mixing chamber, and also the data at the outlet of the mixing chamber. So we have at the inlet, after the first inlet, we have T1 equal to 60 degrees Celsius, T2, the second inlet, T2 equal to 10 degrees Celsius, and the outlet condition will be T3 equal to 45 degrees Celsius. And the pressure inside the mixing chamber is equal to 150 kilopascal. So we will have M1 dot represent the mass flow rate at the inlet, at the first inlet, M2 dot represent the mass flow rate at the second inlet, and M3 dot represent the mass flow rate at the outlet of the mixing chamber. Due to the steady stream process involved in this mixing chamber, so dE system over dt will be equal to 0. So for the mass principle of mass balance equation, dmc dot over dt also equal to 0. And we have the ratio, the mass flow rate ratio between hot and hot to cold water, m1 dot divided by m2 dot equal to y. Y represent the ratio, the mass fraction of the hot to cold water ratio. So mass balance equation, total mass dot in minus total mass dot out equal to dmc over dt for the steady flow process. So we can neglect dmcv divided over dt. So we'll have m in dot equal to m out dot. So for this specific condition of the mixing chamber, so in terms of mass balance equation, we'll have m1 dot plus m2 dot equal to m3 dot. Okay, for energy balance equation, so we have the term for E mass in and also E mass out. So for this case, we'll have m1 dot multiplied by h1 plus m2 dot multiplied by h2 equal to m3 dot multiplied by h3. So this is what I call the energy balance equation for this problem. Okay, so rearrange the equation. So we'll have by using the the mass balance equation. So we'll have m1 dot multiplied by h1 plus m2 dot multiplied by h2 equal to m1 dot plus m2 dot multiplied by h3, where we replace what I call m3 dot with m1 dot plus m2 dot by referring to the mass balance principle. Okay, divide the equation with m2 dot. Okay, we already defined the ratio of the hot to cold water, where m1 dot divided by m2 dot equal to y. So now we will have this kind of equation where in terms of the mass flow rate ratio, y h1 plus h2 equal to y plus 1 h3. So rearrange the equation, so we'll get the equation for ratio of the mass flow rate of the hot to cold water that represented by y, where y equal to h3 minus h2 divided by h1 minus h3, which means by referring to the equation, because the question asks you to determine the ratio, so y, we need to determine the value of y, where we need to find out the value of h3, h2 and also h1 in order to substitute into the equation of y. Okay, next, by using saturated water table, we need to check the phase of water at the inlet at state number 1, state number 2, and also at the outlet for the state number 3 before we determine the value of h1, h2, and also h3. Okay, so we know that pressure is equal to 150 kilopascal. So refer to the saturated water table based on pressure at 0.150 megapascal or 150 kilopascal. So we need to determine T saturated, because we know the temperature at each inlet and also outlet. Okay, so T saturated at 150 degrees Celsius equal to 111.37 degrees Celsius. Okay, so just draw a simple TS diagram or TV diagram. So we have constant pressure line at 150 kilopascal. So the value of T saturated is 111.37 degrees Celsius. Okay, now compare with the temperature given for the water at the inlet and also at the outlet. So for the temperature at the inlet, at the first inlet, T1, so T1 is lower than T saturated at 150 kilopascal. So the phase of the water at the first inlet will be compressed liquid. T2 also lower than T saturated at 150 kilopascal, also considered as compressed liquid. And for state number 3 at the outlet, T3 also lower than T saturated at 150 kilopascal, and the phase also compressive case. Okay, so in order to determine the value of H, we need to use the compressive table. However, due to the lower temperature and also lower pressure, data are not available, so we need to make assumption where we assume that the value of enthalpy for the specific for each state will take the value of enthalpy at saturated liquid based on temperature. Okay, so assume the condition as saturated liquid at constant temperature. Okay, so we need to refer saturated water table. H1 will be equal to HF at 60 degrees Celsius. H2 will be equal to HF at 10 degrees Celsius, and H3 will be equal to HF at 45 degrees Celsius. Okay, now by using saturated water table based on temperature table, so now we want to determine the value of enthalpy for state number 1, state number 2, and also state number 3. Okay, so this is the saturated water table based on temperature. Okay, so H1 equal to HF at 60 degrees Celsius equal to 251.13 kJ per kg. So we can obtain directly from the table. H2 equal to HF at 10 degrees Celsius equal to 42.01 kJ per kg. H3 equal to HF at 45 degrees Celsius equal to 188.45 kJ per kg. So we already obtained all the value of enthalpy for each state. Okay, based on the equation for the ratio of hot to cold water, so we can substitute all the value that we have for H1, H2, and H3 into the equation of Y. Okay, so we'll get Y, the ratio of mass flow rate, equal to 2.33.